Okay, good afternoon, everyone. Before we start, just let me make sure all of you over the weekend, you guys must have received an email that has information about the final. Just so your final exam is next Tuesday, a week from today. Tuesday, May 4th, I think it will be. And the exam will open. So exam open at 12 p.m. and closes at 3 p.m. which is the scheduled time in your syllabus. Yes. Okay, so this is scheduled time in your syllabus. So open at 12 and closes at 3 p.m. I want all of you to have your camera on during the exam. And the Zoom link is most probably the same Zoom link that we use for the class. Okay, so you will have the Zoom link, which is the same one we use for every time we meet. And what else? The exam is comprehensive. You guys have a review on Brightspace, so you have you go ahead and start working on it. Today we'll finalize the material, and next time we start the review. So I will do a lot of review with you, plus the quiz, that what you decided. Okay. So next week, the quiz is on Thursday, Alicia, because that was the vote in class. So next Thursday we do the review and we take the quiz. All right. Okay. So that's it for me. Any questions?
Professor, can I make a quick announcement to the students?
Yes, please, Nelson.
Thank you. So next week, so this is our last week of session, so I did want to make it known that we're having our last two SI sessions this week, and we'll be reviewing old quizzes and exams to prepare for the final. And then next week, this is optional, but I did want to make it known that if the students want, that you guys can decide whether we have a 2-hour-long session before the final exam to go over the review. So if that's something that you're interested in, just send me like a message on the chat, and then I'll let the office know that we'll have a 2-hour-long session to prepare for the final.
Okay, did you hear him very well? But please get ready yourself. I mean, don't wait for the last minute. It will not do you any good. Please start getting ready. All right. So this take care of business. Now questions. How did the homework go? What questions do you have about the homework? Please put them on chat. I'm listening. I mean, listening, looking, whatever. So, okay, 4.1, number 9. Sorry. Okay, 17, Leah, from which section? Okay, so 4.1. All right, so 4.1, we're going to look at number 9 and number 17, and then I will move on to the problem from section 4. Leah, make up your mind.
I'm so sorry. I did not mean to put that. It's 4.2, number 17.
Okay. All right. So, okay, so we'll do those from 4.1, and then I will do that. Okay. So we start with 4.1. Okay. And so it's number, which one? Number 9. Okay, we look at number 9. So we need, so it's number 9, section 4.1. And as I move on, please let me, tell me what to do every time. So we need to solve the following equation. 2 times, so it's this dot means you multiplying 9 to the 3x minus 4 equal 15. Okay, and we have to solve this for x. All right, so what is the first step? So please you tell me on chat, what am I supposed to do every time, just to make sure all of you are working with me. What's our first step in this process? Remember, we have to solve for x. Okay, step number 1, isolate the exponential. To isolate the exponential, we have to divide by 2. So this will give me 9 to the 3x minus 4 equal 15 over 2, which is 7.5. It's an easy number, so I can replace it by 7.5. Now, once I isolate my exponential, I have to isolate it, then I take the log from both sides. So take ln from both sides. Okay. So it means ln of the first equal ln of the second. Now 15 over 2 is 7.5, and it's a terminal, so it's nice to write it this way. And here I will have 9 to the 3x minus 4. All right. Now I use the property of the log, which tells me that the property we're going to use is that if you have, I put it in red, ln of a to the n, you can bring down the n times the ln of a. So this I can write it as, this is my power. I mean, that's what's playing the role of n. I mean 3x minus 4 times ln of 9 equal ln of 7.5. Okay. Now I need to solve for x. You know, so somehow I want to free up x. X is not free in this problem. So one way we can free up x is to do what? What do you want me to do? How can I free up the x? I want to solve for x. What shall I do? Please write on chat whatever you think I should do. Okay, divide by ln, absolutely. So divide by ln of 9. This will free up totally my x. So I divide by it. I'm going to have 3x minus 4 equal ln of 7.5 divided by ln of 9. Now we are in a very good shape because it's a simple problem. So I will have 3x minus 4 equal. Now to make it easy, I'm going to evaluate this to 3 decimal places. So we're going to do it to 3 decimal. So I will have ln, okay, let me clear this up, 7.5 divided by ln of 9 to 3 decimals. So I'm getting 0.917, and that's a 0. So 0.917. Okay. And now the rest become relatively simple. I need to solve for x. I add 4 both sides. Okay. So it means that 3x is 4 point that. Then I need my x. I divide by 3 both sides. And then I just plug in the final answer into the calculator and I figure out my x. So I will have, okay, I'm going to put up, I have 4.917. Divide this by 3. I'm getting 1.639. 1.369.
On the quiz, are you going to tell us how many you want us to round to?
Yeah. And if I don't, because sometimes I forget, you guys make sure to ask me on chat. All right?
Okay.
I will try to remember. In case I don't, please make sure to remind me. Okay? So now we're going to look at number 17, and then I will move on to section 4.2. Right?
17 is in 4.2.
What?
17 is a part of 4.2.
Okay. But I will do both, just to, make sure you guys know everything. So I will keep this in mind. So I'm still going to do number 17, unless you guys are comfortable with it. Oh, I'm sorry, there is no 17 in 4.2. What am I talking about? All right. So I will move to section 4.2. Okay, and I'm going to start with number 10. And then we proceed. Okay, number 10. Okay. All right, so we're going to put it in front of us. We're going to read it, and then we will do it. So a town is growing at a rate of 4% per year. So that's the rate. So every year is 4% of more than the year before. So whatever it starts, and it gains 4%. It's growing. So we have more now. Then it will grow by 4% of the new value, and so on and so forth. What is the doubling time for the population of the town? So what's the doubling time? It means how long will the population take to double in value? And as I mentioned last time, if you guys remember, I told you that the doubling time doesn't depend on the initial value. It actually depends on how fast the function is growing or how slow it is growing. Okay. So let's see how we're going to handle this problem. So the picture is like that. We have a population. It starts somewhere, I don't know what, because it doesn't matter for doubling time, and it's growing because it's growing at 4%. At some point, it doubles in value. What does it mean double? If it's A, doubling, it means it becomes what? It becomes what? Doubling means it becomes what? Twice that much. So if it's A, doubling, it means A plus A. It means twice that much, A plus A. So the question is, how long does that take? Okay, doubling means twice that much. So if, let us say, start with 100, doubling time, it means when it will reach 200. If it starts with a 150, doubling time is when it reaches twice 150. It means 300, and so on and so forth. So how we are going to find the doubling time? So first I'm going to introduce a function. I'm going to call let f of t be the population at time t. What they are giving us is that the growth rate, the rate is 4%. It means every time it grows by 4% of what it was before. So what's the formula for the population? I don't know the initial value because I don't need it. So it's going to be, I'm going to keep it A. So I'm going to call A the initial value times B to the T. That's the formula. But what is B? B is 1. I have a growth, the population is increasing, so it's 1 plus the growth rate. Now the growth rate is 0.04. It means 1.04, all right? So it means f of t is, the function is, its initial value that I actually don't know times 1.04 to the power t. So that's the formula for the population. Find the doubling time. Means we need to find doubling time means we have to find the t such that the population is twice what it started with. Twice what started with, it means 2a. So what we're going to do is we're going to set f of t equal to a and solve for t. All right, so back to a problem that we've been working on. Step number 1, we have to isolate the exponential term. So we're going to divide by a. And that's where the a disappears. And this tells you that we don't need the a. So I will have 1.04 to the power t equal. It's 2a, but I'm dividing by a. It means 1.04 to the t is equal to 2. So we'll be able to solve for t regardless of what a is. So now I need to solve equal ln of 2. Now again, t is my exponent. The property of the log is going to bring it down. I'm going to have t times ln of 1.04 is the ln of 2. And I will finish here. It means my t equal ln of 2 divided by ln of 1.04. And let's see what is the doubling time. Now, 4% is not a very good rate. So let's see how long it takes. So I'm going to pick up. Basically, I'm going to evaluate ln of 2 divided by the ln of 1.02. Sorry, ln of 1.04. Okay, so ln of 2 divided by ln of 1.04. And I'm getting 17, a little bit over 17 years. Okay, that's the doubling time. It means that's how long will it take the population to double in value. And as I said several times by now, it doesn't depend how much you start. If you start with 100 million, it's going to take 17 years to double, to become 200 million. If you start with 50,000, it's going to take it 17 years to grow to 100,000. What really decides is the rate, how fast it's growing. So if it grows at 4%, that's the doubling time. Okay, please ask question as we move on. Okay, now let's do number 11. Now, if you guys didn't finish writing while I'm working, please let me know. So let's look at number 11. All right. Okay, number 11 is basically the same idea. The population is decreasing at a rate of 7%. So we have to be careful now. It is decreasing. So I underline that. It means the growth rate is negative. We have negative growth. How long does it take for the population to be cut in half? I mean, it makes sense. If it's decreasing, it will never double. It's going to be actually, it's decreasing. So again, I have the same issue here, but my function is going down. That's my function. That's my population. It starts at a certain A that is not going to be relevant in this problem. And the question is, when would the population be cut in half? It means I need to find the time where this one should be what? What this should be. Cut in half. It means we have to find the time where the population is what? What this point should be on the graph? Anybody? Cut in half. It means the population is half of A. It means A over 2 or a half of A. That's really what it means. So now let us proceed. So again, it's the same problem. I'm going to introduce f of t, which is population at times t. And f of t is A times b to the t, because it's by the same percent. Now to find b, what do we know? They gave me that the growth rate is decreasing. It means we have a negative growth. And it's decreasing by 7%. It means the growth rate is minus 0.07. The b, it means every year is losing 7%. So basically it means what remains is 93%. So every year is 93% of what it was. That's going to give me 1 minus 0.07, which is 0.93. So now again, the same problem. My function is A times 0.93 to the power t. Another problem is the same ideas. We need to find t such that f of t is cut in half. It means a half times A. The rest shouldn't be hard for us at all. Again, we divide by A across. A will disappear. I will have 0.93 to the power t equal a half. I take the natural log from both sides. I bring down my t. One half is 0.5, so it's easy number. And then I get my t here. It's ln of a half divided by ln of 0.93. And that tells me how long it took for it to be dropped by a half. So ln of 0.5 basically divided by ln of 0.93. And I'm getting 9 point, I don't know if you guys are doing it, 9.55. So it's a little bit, see, it's 9 years and a half years. Okay, so it's gonna take that long for the population to be cut in half. So if it keeps decreasing at the rate of 7% per year, after 10 years, half of the population is gone and half actually is remaining. Okay. All right, any questions? All right, so let's look at 14. 14 is verbatim like the problem I did. So I will let go of it. It's verbatim the same. I will assign it for next time so you guys get the chance to practice it yourself. So I will assign it as a practice problem for next time and try to make sure you do it. It's verbatim what I did there. So if you cannot do it, I will definitely go over it next time. And I will look at number 17 because it's slightly different. All right. So I will read it and then I will give you a minute to interact with it and then we see what to do with that. So number 17 is the half-life of plutonium-239, which is a radioactive element, is 24,110 years. That's the half-life. It means that's the amount needed for this chemical to actually be cut in half its value. By what percent does a sample of plutonium decrease after 1 year? So I read one more time and tell you what is given and what do we have to find. They're giving us the half-life. They're telling us how long it takes for the plutonium to become half its value. But they're asking us by what percent does it decrease? It means they are asking us for the growth rate. So what's given is the half-life. What we're asking us is the growth rate. So let's write this down. And the question is, how are we going to relate these two ideas? I mean, what can we do to solve the problem? So number 17. Okay, what's given to us? What's given is that the half-life is 24,110 years. That's what's given. They told us that. What do we have to find? We have to find the growth rate, which is going to be a negative growth because whenever there is a half-life, it means things are decreasing. We have to find the growth rate, okay? And as a hint for those who look at the practice problem, I tell you start by finding the growth factor. Start by finding the growth factor B. Once you find B, if you know the growth factor, you know the growth rate immediately. Okay, so how shall I set up my problem so that I will be able to find the B? Okay, so it's a little bit harder than the previous problems, but it's not really impossible. So the question is, so I have that, I'm going to use it to be able to find the B. I'm going to use that to find the B. So how can I do that? How can I use those two? I'll give you a minute to really try to think about it a little bit. And the only thing I will start, we're going to say let f of t be the amount of plutonium after t years. So t equal to 0, we don't know what it is, but we're not going to worry about it. Then f of t, the only thing I know that f of t is exponential, even though they didn't tell us, but they are assuming that. It's a times b to the t. Now the question is, I stop right there myself. How can I use that to find the b? I give you a minute to interact with it. Use what you know to find what you don't know. I'm giving you a hint. Anyone who has an idea, let me know.
Do you set it to equal the half-life? So set A times B to the power of T equals 24,110?
No, you're not. No, you're not reading the problem correctly. What's the unit of that? Years. It means in the picture. Watch what the picture is. Whatever it starts, it's decreasing. The half-life is that much. It means when T is that much, that's the half-life. This is half of A. I want you to look at the picture so you understand the problem. Now I let you go. What's the setup here? So the half-life, it means the time needed for the population, for the plutonium to decrease to half its value. How can I make use to that? Means that if you plug in 24,110 here, what is the amount of plutonium at this time? The half-life, it means after that much time, the amount is going to be how much? Half of what started with. So that's the key to do this problem. So the half-life is 24, means that if you evaluate the amount after that much, what you have is half what you started with. And now I'm going to use this equation to be able to solve for T. So it means that if I take A times B to the power 24,110, I get half of A. So 24,110 is not the initial value at all. It has nothing to do with the initial value. 24,110 is the time. It's not, it's in years. It's the time needed for the plutonium to become half of what started with. So suppose in the 1900, whatever T equal to 0 is, we had that much. After 24,110 years, it means that, so this should be, long time ago. It takes 24,110 years to this one decay to half what it started with. So whatever this start with, after 24,100, we have half A. The question is, how slow is it changing? How slow it is changing? So that's really the setup. And now we're going to solve for B. Okay, so T is the time needed for this to occur. Okay, now how to solve for B? So I need to isolate this expression. We're going to divide by A, both sides. And then this will give me B to the power that much equal a half. Now we solve for B. Now let us note that this is not, the unknown here is not exponent. So we don't have a T in here. So I do not use the logarithm. To solve for B, I have to use a root. It's a weird root, but it's that root. And then I find my B, which is a half to this power. So it means equal to 1/2, which is, so it's 0.5 to the power 1 over this huge number. It's going to give me 0.9999, and I will not round it here to 4 decimal because I don't want it to be 1, because I want it actually to decrease. So that's really my B. So now my growth rate. So this is 1 plus the growth rate. The growth rate is how far is this from 1. So the growth rate is this expression minus 1. Now, if it's taking 24,110 years to decrease to have its value, it means it's decreasing at a very, 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 very small rate. Otherwise, the half-life will be much more than that. So since it's taking that long, it means the rate is very slow. So the rate is going to be this one, 99997 minus 1. It means the rate is going to be minus 0.0000123. So that's really the rate at which it's decreasing. It's a very, very slow rate, which makes sense because the half-life is huge. It's 24,110 years. Okay, so it's a problem. It's a bit harder than the others. That's why that's the one I wanted to do. Okay, so let us sum up the idea here. They gave me the half-life. They want me to find the B. So the idea is that how can I use this information to be able to find the B? All right, okay, the way we use it is said, okay, the function is exponential, that's the formula. And I want B. I want the growth factor because if I know the B, I know the rate. So, okay, what is given to us? What's given to us is that after that long, the amount is half what it started with. And this is the equation I need to be able to solve the problem. And then I plug this here, A times B to this power, because this is time. This is not initial, that's the time, half A. And then I solve. So I get this weird equation. All right, so the only way to solve this, because the power here, that's not an exponential, because there is no unknown in the power. I took it to the root. So, and the root is a huge root, 24,110. Plug it into our calculator and find the B. Once I find the growth factor, the growth rate will follow automatically. Okay. Please, questions along those lines. Number 15, I think, is the same thing. So I will assign for next time for you guys to practice. I will assign number 15 and the one I didn't do, number 14. And I'm at number 18 and number 14 for next time, so you guys can get the chance to practice those problems. Okay. Any other questions before we proceed for the last idea in this course? Questions? Okay. The last idea is the following. We wrote exponential in the form A times B to the T. Today, we're gonna learn how to write them in a different way. So another way to write, so that's really the idea, another way to write an exponential function. An exponential function. Another way to write it, okay? So far, how did we write an exponential function? So far, up to now, okay, we wrote exponential in the form. So we wrote exponential function in the form A, the initial value, B to the T, okay? Today, what we're going to do is the following. We're going to rewrite. We can rewrite. And the word rewrite is important. We're not going to change anything. We're going to rewrite A times B to the T in the different format. A e to the k t. Okay, so we're going to take the way we wrote it, and we're going to write it in a different format. So now the reason is that why this bother. All right, this is our preferred form because this one we understand. In calculus, this is easier to use. And that's why we have to learn that this function here, when you ever see it in a calculus class, is exactly the same thing as that. But we have in the example, we're going to see what's the connection between them. But you will see that exponential function for you will be written either this way or that way. And they are both exactly the same thing, but written in a different format. So let's see what's the relationship between those two ways of writing an exponential function. So I'm going to do that by an example. So suppose I have a function f of t written in my regular format, like 1000, 1.2 to the power t. That's the format we know. So that's a function where the growth rate is 20%. So my b here is the 1.2. I'm going to manipulate it, so I write it in this form. Okay, so let's see how I'm going to do that. I'm going to do the following. Let me recall a fact. So it's kind of tedious. Recall that if I take e to the ln of 1.2, this gives me what? Back to you. If I take e to the ln of 1.2, this will give me 1.2 back. Okay, so 1.2, e to the ln of 1.2 are exactly the same. So we're going to do the following. We're going to substitute e to the ln of 1.2 for 1.2 in the expression of f. In the expression, sorry, for f. Okay, so my goal is to show you where this whole formula at the end is coming from. So let's see what this will give me. It's going to give me the following. That f of t will become f of t, which is 1000, 1.2 to the power t will become 1000. Instead of 1.2, I'm going to put e to the ln of 1.2. Notice that I haven't changed anything. Okay, I'm not really changing. I'm going to basically write it in this form. And that's really the mathematics behind it. All right. Now I need one more fact from an exponent before I finalize this. So the fact is the following. If I have a to the n, and I raise the whole thing to the power n, this is going to give me a to which power? So before you answer, let me make sure that you know what I am asking you. Suppose I have a square to the power 3. Okay, this gives me a to which power? Back to you. And what do we do with the power? Think a little bit. Power 6, we multiply them. We multiply them because it makes sense. This is a square times a square times a square. So how many a square we have? 1, 2, 3. We have 3 of them. So that's give me a to the power 3. So whenever I have a n to the m, we multiply the power. I'm sure I mentioned that before, but I need it now. So why is this relevant here? It means this is going to be written like this. E is a number. That's my a. To the power ln of to the whole thing to the power 2, this I can write it like that format. Times t. Okay. So if I evaluate now ln of 1.2, I'm going to evaluate it by picking up my calculator and evaluate that number. I will get 0.1823. Okay, so it means that my function can be written there. 1000 e, this is 0.1823 times t. Okay, so this function, I rewrote it. I'm totally manipulating it under this format. Okay, so 1000, 1.2 to the power t, I was able to write it. I was able to write it into the form 1000 e to a certain kt. And what's playing the role of this symbol here is nothing more than the ln of 1.2. So our first formula will become the following. So every function that could be written a times b to the t, I know it's kind of weird, but we have to learn it. b to the t, I can rewrite it as a e to the kt, where k is nothing more than the ln of 1.2. That's where this formula will come from. Okay, so if f of t is written as a times b to the t, then we can write f of t. F of t could be also written as a e to the kt, where the k is ln of b. So every function written this form, I can rewrite it, I'm not changing it, as a e to the kt. And what's played the role of this k is the ln of b. Part 2 is, before I give you a lot of examples so you guys are comfortable with that, I would like to do the following. Part 2 is, suppose somebody gives you f in this format. How can I go back to this format? So how can I actually see that this is exactly that? In what sense? So part 2 is the following. Suppose that f of t is given in the form in the following form. A times e to the kt. And the question is how to rewrite it in the form a b to the t. So we're learning how to go back and forth. All right, so let us listen a little bit. I'll show it to you by an example. So suppose I have a function f, and somebody tells me f is, let us say, 1,000 times e to the power minus 0.03 t. We've never seen anything like that. I'm going to take this function and write it in the form that we know. Now, first, let us understand what's the k in the picture. The k is what t is multiplied by. So in this scenario, the k is what t is multiplied by. So the k is the minus 0.03. Now the question is how I'm going to get here. All right, again, we're going to play a game that will help me to write it this format. This is my game. I'm going to write this as 1,000. And I'm going to use the property of exponent to write this expression into this form. I'm going to raise t. Since this is multiplied by that, e to the minus 0.03. So we're really playing a little bit of a game by rewriting this power like that. And now this is going to be my b. This is going to be actually the b that I'm going to be after. In other words, it's going to be equal to, let me compute e to the minus 0.03. That's actually a number, and we can evaluate. That's evaluated. This is 0.9704. So it means that this is going to be written as 1,000 times 0.9704 to the power t. So if a function is given to you in this format, e to the kt, where k is what t multiplied by, this could be rewritten as a b to the t. So those basically are exactly the same functions, the exact same thing written into different ways. And exponential function will be given to you sometimes that format and sometimes this way. And we should be able to go back and forth between them. So let me make a summary of all this, and then we practice those ideas. So a summary. Please, if I move the paper and you're not done, I will appreciate it if you guys help me out and tell me, slow down. Okay? So summary. Any exponential function. Any exponential. It means a function that grows by the same percent. Any exponential function can be written in the following form. Two ways of writing it. A, b to the t. That's the form we're used to. It also could be written e to the kt. Okay. Now, if we know b, suppose we know b, then k, to find k, is going to be the ln of b. And if we know k, then b is what we did here. If we know k, the b is e to the k. That's what's going to be the b. Then b is e to the k. So if I give it to you in this form, you can rewrite it like that. That's your k. If I give it to you in that format, you can write it this way, and that will be your b. Now, some terminology. K has a name. K is called continuous. We add the word continuous growth rate. Okay. Everything else remains the same. It means B is the growth factor. Okay. So K will be given a name, which is continuous growth rate. B is the same B, is the growth factor, which is 1 plus the regular growth rate. Nothing has to do with continuous. Okay, so that's really the summary, and now we're going to practice it a little bit. So you guys will be comfortable moving back and forth between those two ways of representing basically the same function. All right, so let us do some examples. Right? I'll put the problem and you guys do it as usual, and then we check it. So question number 1 is, write the function f of t equal 500 times 0.9 to the power t in the form f of t equal a e to the kt. Okay, I want you to write this one in this format. You have the summary in front of you, and I give you a minute to write it down. See if you guys got it. So this is written b to the t. I want to write it e to the kt. What is going on? So basically, I want to write it this way. A always remain the same. I want to write it under like that. So what is the k? The k is ln. So here b is 0.9. It means k is the ln of 0.9. Okay, now the ln of 0.9 is a number that we can pick it up. It's minus 0.1054. It means that f of t could be written 500 e to the power minus 0.1054 t. That's how I can rewrite it. So this is the way we can rewrite this function. Now, the idea is those two are exactly the same. What do I mean by exactly the same? If I put t equal to 2 in this expression, I put t equal to in this expression, I get the exact same answer. I put t equal 5 here, put t equal 5, I get the same answer. I pick up my calculator, I graph this function, and I graph this function, I get the exact same function. So this means that those are the same, but written in a different format. Now, the terminology. What's the continuous growth rate? So you guys are familiar with the terminology. The continuous growth rate is the K. That's what we mean by the continuous growth rate. So whenever you hear the continuous, it means you have to go after the K. It's that much. And now, what's the growth factor? And finally, what's the growth rate without any continuous attached to it? The growth factor is your B, which is the 0.9. The growth rate is what the growth rate is how far B is from 1. So remember that this is, first, B is less than 1. It means we have a decay. So that's 1 plus the growth rate. So the growth rate is going to be 0.9 minus 1. It means minus 0.1 or minus 10%. So that's a quantity that represents a decay by 10%. Every year we are losing 10% of what we have. Okay, so that's how we move from a b to the t to a e to the kt. Now I'm going to take you backward. We're going to take 2 examples where we have to move backward. Okay. Example number 2. Let f of t equal, okay, initial value is not important. I can write anything. E to the 0.2 t. Question is, write in the form a b to the t. So I have it in this format. I want to write it in that format. Now, the first thing is I want to make sure that you understand what k is in this whole picture. E to the 0.2 t. What is the k in this picture? Put it on chat if you guys can find it. If not, let me know. Anybody else? Right. So the k is what t multiplied by. That's the 0.2. That's really what my k is. Now, the question is, I want to write it into this format. So I have the k. I want to write it into this format. How can I write it in this format? What's the b? The b is this piece right there. That's the b. It's the e to the 0.2. That's the b in this picture. So the b is e to the 0.2, so which is 1.2214, because just pick, and then this would be 500, b, which is 1.2214. So this function, e to the 0.2, is actually our regular exponential, where this is the growth factor. So now, terminology. Continuous growth rate. Growth factor. And the regular growth rate. Okay. To know the continuous growth rate, we need the k. So the continuous growth rate here is the 0.2. What's the growth factor? Please put it on chat because I need somebody to do some work for me. What's the growth factor? Okay, if I don't see an answer, it means somebody is struggling. What's the growth factor? The growth factor is our old b. Nothing new about it. What's the growth rate? Again, the growth rate is the growth rate that we know. Nothing changed at this stage. What's the growth rate? 0.2214. It means 22.14%. So that's a quantity. Did I go very badly? No, it's 22, right? It's 22.14%. Okay, so it means that represent a quantity that is decaying, that's growing at this percent. So my last example, I mean, according to those lines, just to make sure that you guys can go back and forth. Suppose now I have f of t equal, let us say 50 times e to the power minus 0.123t. Okay, and I wanted to write in the form ab to the t. Okay, all right, please, all of you, just do it. And tell me what you get. First, we identify the k, and then I use it to find the b, and then I have my problem. Okay, what's the k in this problem? What is the k? You're too quiet today. What's wrong? I know it's the last week, so, but you're too quiet for it. That's the k. What's the b? What's the b? Anybody? Okay, I'm getting 0. Exactly 8842, which is e to the power that. All right, so far so good. Now, the terminology. What's the continuous growth rate? What's the growth factor? And what's the growth rate? Okay, all of you. I mean, I want answer on chat. Continuous growth rate, what do we mean by that? That's the K. That's the K. That's the continuous growth rate. What's the growth factor? Quickly. It's the B. The B, that's the growth factor. And the growth rate, for me, that's the best because that's really explained to me what's going on. It tells me by what percent is my quantity increasing or decreasing. Give me the growth rate. I mean, I have to compute it myself also. Give me the growth rate. Okay, all right. This is 1 plus the growth rate. That's the growth factor. It's basically how far the growth factor is from 1. So the growth rate is going to be 0.8842 minus 1. We have a decay because the B is less than 1. And I will copy whatever answer you guys are giving me, minus 0.1158, which is correct. It means minus 11.58%. It means now we understand that this represents, when you write it e to the kt, it's hard to fully understand it. When we write it this format, we fully understand. This is a quantity which is starting at equal to 0. Its value was 50. And it's decreasing at the rate of 11.58% per year. It means every unit of time, it goes down by 11.58%. And that's the benefit of really writing it b to the t. That's the benefit of it. We understand it better. But as I said, calculus is easier with this format. So we should know that both represent the same thing. Right. Now, note about the effect of k on the graph of the function. So let us recall one thing. Suppose I write f of t as a times b to the t. Okay. Now, if b is greater than 1, we have is increasing. If b is less than 1, then it is decreasing, and b is always positive. Okay, so when the growth factor bigger than 1, my function is increasing. When the growth factor is less than 1, it is decreasing, and this is the initial value. Now the question is the following. Suppose f of t is written as a e to the kt. When do we know whether it's increasing or decreasing? All right, so for a b to the t, the b explain the concepts. E to the kt, how do we know? Just by looking at it, whether it's increasing or decreasing. What about what's really into the picture? All right, the idea is the following. Let us remember that e to the that b is e to the k. Now, two things happen. The exponential function, so if I draw the function here, e to the x, the following happens. This is bigger than 1 when k is positive. Means if I take e to a positive number, like e to the 0, we know it's 1. If I take e to any number bigger than 0, like whatever, 2, I get a number bigger than 1. However, if I take e to a negative power, like if I take e to the power minus 1, this is 1 over e, it's a number less than 1. So this is less than 1 when k is negative. So suppose b is e to the kt. If k is positive, e to the k will be bigger than 1. If k is negative, e to the k will be less than 1. So this will give us the following effect on the graph. If k is positive, we have an increasing exponential function. If k is negative, then we have a decreasing exponential function. Because what happened in this scenario, what happened in this scenario is really the k. Positive k make the b bigger than 1. We know that e to the 0 is 1, e to the 1 is bigger than 1. If k is negative, taking a to a negative power is like 1 over b is a number less than 1. So this is really what tells us about increasing or decreasing if you have e to the kt. And that's important to know, absolutely important for us to know. So both aspects are important for the graph. So now if I give you any exponential function, regardless how it looks, just by looking at it, we should know whether it's increasing or decreasing. So for example, the example that I took previously, so suppose I take this one, 500 e to the 0.2t. My k here is positive, it's going to be increasing. And notice, when I computed the b, I get a number bigger than 1. Because if you take e to a positive number, you're going to get a number bigger than 1. That's really what's happening mathematically. Now, example number 2, when I take k to be minus 0.123. If I take e to a negative power, I get a number less than 1. This is going to be a decreasing function. So the k tells me whether it's increasing or decreasing. So let me give you a bunch of k's, bunch of examples. Tell me if it's increasing or decreasing. So 50 is not really important. E to the power, I don't know, 0.02t. F of t equal 50.28 to the power t. And the question, increasing or decreasing? Just by studying. Okay, I start with the first one, increasing or decreasing quickly. positive, increasing. It means if we graph it, we get an increasing function. This one, increasing or decreasing quickly. Quickly. This is a, b to the t. What's the b here? B is 0.8. This is less than 1. It means decreasing. So do not confuse the K and the B. Very good. Here, K is minus 0.02. Negative, decreasing. Finally here, B is 1.2, bigger than 1, increasing. And that's absolutely crucial for us to know the effect of K on the graph, which K give me an increasing function. So like this one, immediately it's going to look like that. This will look like this. They're all exponential, have nothing to do with a line. This one here is going to go like that. And this one here will go, oh, sorry, did I goof? Decreasing, my apology. I'm going faster than I want to. That's decreasing. This one will go up. Okay, so that's really the effect on the graph, right? Okay, the last thing is we're going to do an example where I'm going to throw in the word continuous to show you how you work with that. So suppose I give you the following scenario. All right. In 1995, let me take a new page. In 1995, the population in Washington State was 5.4 million. Okay, and it's growing, and it's growing. So the population is increasing. Okay, the continuous growth rate of the population. So here I use the word continuous. The continuous growth rate of the population is 0.030. Okay. Question number 1. Find a formula for the population at time t. And the goal of this problem is to emphasize, find a formula for population at time t. Okay. Now, they're giving you continuous growth rate. And a lot, sometimes book, they tell you continuous. When they tell you continuous growth rate, it means they are giving you the value of K. That's what you should understand. It means the K is 0.013 and it's growing. It means your K is positive. That's how we understand that. The initial value is 5.4. So at time t, where t is number of years after 1995. Right. So now the formula for the population would be, the initial value is always the same, but this problem gave you the K, did not give you anything else. E to the power 0.13. So that's the formula for the population. So if they tell you the continuous growth rate, if they use that word continuous, means they are giving you the K. They're not giving you the regular growth rate. Okay, now let us probably keep going. So suppose I tell you, find the population in the year, okay, what year we are now? 2021. Right? So what should I do here? So suppose this is the growth of the population. Now what's the population in the year 2021?
Do you plug in 2021 for T?
No, not 2021. Be careful. Be careful. What's T? What's the initial year? In 1995, the population was 5.4. Yes, exactly. And T is the number of years after 1995. All right, so 2021 correspond to which value of T? You take basically the difference. It means how far is T is from 1995. It means everybody is telling me is 26. So I plug in 26 for T, not 2021, because T equal to 0 is the year 1995. So now the population would be, you guys computed because I didn't, and tell me what the answer is. E, so I'm gonna work with E because that's what I have, 0.013 times 26, all right? So how much did you guys get? My advice to you is first evaluate that, or be careful with your calculator. So first I'll evaluate the power so I don't do any mistakes. So I have 26 times 0.013. It's 0.338. And finally, I will evaluate that. So it's 5.4 times e to the power 0.338. Now, of course, it has to be more than 5.4 million. Okay. So according to this model, the population in Washington State this year should be 7.57 million. We should Google it and see if our pattern works. All right, my last question is, when will the population reaches, let us say, 10 million? What should I do now? When will the population reach 10 million? What do you want me to do? Quickly, we have 3 minutes and we should do it in 3 minutes. Okay, we're gonna set the equation equal to 10. So we're gonna set f of t equal to 10 and solve for t. So when it is, all right, so what is f of t? F of t is 5.4 e to the power 0.013t equal to 10. So we're gonna set equal to 10 and solve. Right? Now we've done, of course, those kind of problems. Let us do that. Okay. So how do we solve this? We need to isolate the e, and so we divide by 5.4 equal 10 divided by 5.4. Okay, and then we take the natural log from both sides. So this gives me e to the 0.013t equal to that. And now I do the same thing. This is, I'm going to bring it down. So this will give me 0.013t ln of e, but ln of e is 1 equal ln of 10 over 5 pound. Now ln of e is 1, our honest to goodness 1. So it means I will get 0.013t equal the ln of that. We can evaluate it or we can hang on to it for a little bit. And then I need t, I divide by 0.013. Okay, 10 million. So t is, I don't know if anybody did it. So it's ln of 10 divided by 5.4. And the whole thing divided by 0.013. 13. I'm getting 47.39 years. It means in the year, so t equal to 0 correspond to 1995. So it means almost 1995 plus 47 means almost in the year 2042. Okay, that's when the population will hit 10 million, almost 2042. Okay. Any questions? All right, so I stop at this stage. For Thursday, you will have a quiz, and I put on bright space what you are responsible for. Basically, everything we've done with how to solve an exponential function and how to do problems like this, how to move back and forth between this conversion problem I'm doing. So please do your homework for Thursday, and so do your practice problem to get ready for the quiz, to do the practice problems. And bring the review with you. So I will review as much as I can. And finally, you guys will have your quiz. So everything you do now is good for your review. So if you study for this quiz very well, this already helped you a lot for your review. Okay. Right. Yeah, we will review for the final next Thursday. Absolutely, Amanda. Absolutely so. Any other questions?